In this video, Finding the Electrons, we're going to look at how scientists were able to locate electrons within different orbitals. So how are we able to do that? So scientists have studied the light generated by different elements to determine how the electrons in the element is arranged. So we know that you can have a helium light bulb, you can have a neon light bulb. We also have what we would consider a white light bulb. So the way scientists looked at this was we took a light bulb and we shined light at a slit. And this slit is going to allow you to organize this light. Then the light will go through a prism, basically a fancy crystal, which is going to allow the light to be distributed. And then we can see a rainbow. And in terms of this, what we get is red, orange, yellow, green, blue, indigo, violet. So we have this continuous rainbow for what we would call white light. So white light is the combination of all light, which basically means that there is no one specific element that creates this light. The other thing we can do is change this out to use perhaps a helium lamp or an oxygen, neon, argon, or xenon. So if we look at these objects on the right, these are called line spectra. And so if we look at these, we'll note that the same pattern is observed, but it's no longer continuous. What we start to see are some high wavelength objects at red, yellow, some green, indigo, and violet. But what we don't see is continuous light. The other thing that we don't see is the same lines in all of these different spectra. It's not like helium gets some lines and then the same lines are observed, just more lines. So as we look at this, the question is, what does this mean? So the number of lines increases as the number of electrons increased. So this led to the Bohr model for electrons. So Niels Bohr studied the number of lines for each atom or each element. So he stated that an electron only orbits at the nucleus at specific orbits. Electrons in these orbits, or stationary states, are stable and do not collapse into the nucleus. So he's saying, if we have the nucleus here, if we have several states, what he's starting to say is that the electrons can be in this state here, and he's going to name them n equals 1, 2, 3. And what we're going to see is that the electrons in these orbits are stable. Now, physics tells us that something in an orbit will collapse towards the center, but that is not what we see. And he states that electrons can transition between orbits, but they cannot exist between the states. So if we have these states, what he is saying is that we can observe this transition or this transition. And what he's corresponding his statements are saying, and we're going to explore this in further videos, is that these lines are transitions from the n equals 4 to 2, and this would be from the n equals 3 to 2. So these different lines are going to give us different spectra, which makes sense that elements with more electrons would have more lines. So this gives us an interesting philosophy that electrons are known to be a particle of mass. We have been able to measure the mass of an electron. It is 9.11 times 10 to the negative 31 kilograms. But we know that they can emit energy based as light. So this told scientists that maybe an electron could behave as both a particle and a wave. So in this case, they're going to go back and reconduct this double slit experiment with electrons. As a reminder, you will see an interference pattern if it is a particle, if it is a wave, and a no interfering pattern if this is a particle. So here we're going to have our electron source. And so we are going to get this to come forward, and we are going to allow the electrons to irradiate this. And so what we're going to see is something that looks like this. So this is wave behavior, because if it was a particle, we would have expected something that looked like this. And so scientists were quite confused. So they started to think about different things. The first thing they thought about was, what is the wavelength of this particle? So we know that it's going to have a wave-like behavior, and we know that because we observe this diffraction pattern. So we see diffraction. And if it was truly only a particle, we would not observe this. So when we think about light, so for light, C equals lambda nu. However, electrons have mass. Light particles do not. So we can't use this equation. But de Broglie was able to determine the wavelength of a particle, where this is the wavelength. In meters. This is Planck, and that's a constant. And then we have the mass multiplied by the velocity. And this needs to be in kilograms, and this is going to be in meters per second. So we can determine the wavelength of any particle. De Broglie also states that all particles have a wavelength. So let's look at the different wavelengths of several of these. So if we look at an electron, it has a mass of 9.11 times 10 to the negative 31. It has a quite fast velocity of 2.65 times 10 to the 6 meters per second. And if you were to plug it into de Broglie's equation, we have a wavelength of 2.75 times 10 to the negative 10 meters, which is roughly 2.75 angstroms. This is close to the atomic radius. However, if we look at a football, the standard NFL football is 0.425 kilograms. Drew Brees, a classic quarterback, was clocked at throwing a football at 52 miles an hour, which is 23.3 meters per second. And it has a wavelength of 6.69 times 10 to the negative 35th meters. So it's super small. If we look at a baseball with an average pitch of 95 miles per hour, we get a 1.08 times 10 to the negative 34th meters, which is also very small. If we want to think about something with a much, much greater mass, an F-150, so a Ford supercab truck, it has a mass of roughly 2,000 kilograms. And if it's driving at 65 miles per hour, perhaps down the highway, it has a wavelength of 1.03 times 10 to the negative 38. So all massed objects moving at a velocity have a wavelength. Some of them just have a super, super short wavelength. And so we can't actually observe that. So, but de Broglie allows us to calculate the wavelength of any particle, including an electron. So the result of the double slit experiment really puzzled scientists. So, as a reminder, if we irradiate electrons, we get a diffraction pattern. That looks something kind of like this. So scientists said, electrons have mass. They also happen to have a charge. So we could put a detector right here where we could watch these electrons. So they want to watch the electrons. And so what they did and what they see is actually this. Oops. So they watched the electrons, which means that they knew if it went through the top slit or the bottom slit. But once it does that, now we get particle behavior. So you can slow down the electrons. So if you, we'll make this a little bit smaller. If we have our double slit experiment and we just allow one electron through at a time, we will again see this behavior. So one at a time. And we know that because we can track the detection on the detector. So you can see one electron at a time. So over time, you would get random electrons in random places that would sum up to this diffraction pattern. But if you observe the electron and you know that it goes through one slit over the other, it behaves as a particle. So to date, so these experiments were first conducted many, many years ago, but today you can only observe the wave behavior or the particle behavior. You cannot observe both at the same time. So you can observe either how the electron behaves as a particle or as a wave. This led to Heisenberg to propose an uncertainty principle. This principle says you can either know where it is going, so this is the position, and this is the momentum. So you can either know with accuracy where it is or how fast it's going. So this information is what we would call a snapshot in time. You basically take a series of pictures as to where the electron is. So if we were to think about predicting the path of an electron, if we were to think about the path of a football, so if we have human number one, he has a little football, and he is throwing this football. When the football leaves, it has a trajectory. And our receiver is down here, and he's going to catch the ball. So with a football or a baseball or a ping pong ball, there are no outside influences. This has a relatively steady arc. And if you were to take a series of snapshots through time, it would follow this arc. However, if we were to have an electron, it actually doesn't. So what we actually see for an electron is a series of images, but with a much broader path. So we can start to see this arc where there are lots of different variations. So this is going to give us a statistical value. So we're going to start to think about where is it likely to find the electron. Basically saying, if we can't know exactly where it is or how fast it's going, but we can start to think about where it is most likely to be isolated. So in the next video, we're going to look at where we could find the electron.